Hey everyone, it's Johnny from Prime Academy, and today we're going to be focusing on how we can use the derivative of a function, specifically the first derivative, to create the sketch of that function. So to start, before we do any differentiating, taking the derivative, we're going to look at the original and see what we can find. So I see that this is a rational function. This means that there is potentially a horizontal asymptote and a vertical asymptote. Now, for horizontal asymptote rules, that's something that they're kind of expecting you to know from Advanced Functions 12. And how we do that is we compare the degrees of the numerator and the denominator. And we can see here that the degree of the numerator is 0 and the degree of the denominator is 2. That's based on the exponent on x. Since the degree of the bottom is bigger than the degree of the top, that means that the horizontal asymptote is going to be y equals 0. The bottom is just going to be getting way bigger than the top. So if you have a number like 2 over 1,000, and then 2 over 10,000, and then 2 over 100,000, those numbers approach 0, but never actually equal 0. For our vertical asymptotes, what we're going to be doing is we're going to be taking our denominator and setting it equal to 0. This identifies the values of x that the function is not allowed to equal, because you can't divide by 0. So we would have x squared minus 1 equals 0. Now I'm going to solve this just using basic algebra. I'll stick with the baby blue color here. X squared equals 1, and then x equals the square root of 1, which is plus or minus 1. So it looks like we've got two asymptotes, or two vertical asymptotes, plus 1 and minus 1. Other things you'll need to find with the original function are x and y intercepts. So to find the x-intercept, with any fraction, it's the numerator that tells us what makes the function equal 0. And why am I talking about the function equaling 0? Because at an x-intercept, what we're going to be doing is we're going to be making y equal to 0. And so what we have is 2 over x squared minus 1. At every x-intercept, y is 0, so that's why I have chosen to make y equal to 0. Now, this equation is not solvable. There's no value of x here that will give me 0 for the fraction. So just to prove that, if I cross multiply, this up here and this up here, x squared minus 1 times 0 is 0. 1 times 2 is 2. There's no x-intercept. So we can just sort of erase that and acknowledge that there are not going to be any x-intercepts, but that's something you still want to look for. So I will just write it out. We'll just put D and E. Now for the y-intercept, we just make the x value equal to 0. So we go y equals 2 over, now notice how I've replaced the x with 0, minus 1. Y equals 2 over minus 1. Which equals negative 2. So that means I have a point at 0, negative 2. Now we can actually move on to the derivative part. So I'm going to take the derivative of this function here, and how I'm going to be doing it is actually using the chain rule. I'm not going to use the quotient rule, and that's because I don't have a variable in my numerator as well. So given that I'm going to be using the quotient rule, I'm going to take the expression in the denominator and I'm going to move it up and then put it to a negative exponent. I want to be clear that, I'm going to erase this, that the x squared minus 1 here, that's the same thing. I've just moved it into the numerator and put a negative exponent on it, allowing me to use the chain rule. So that's minus 1. The exponent always comes down in front. There's the 2. We rewrite the original expression, minusing 1 from the exponent, and then times it by the derivative of what's inside, which would just be 2x. So I can just scroll up here if that's okay. What that leaves me with, if I want to simplify this, is negative 4x over x squared minus 1 to the 2. And I want to just be clear here that this x squared minus 1 is the same thing here. All I've done is I've taken the exponent, which is the minus 2, and I've made it positive again because I put it back in the denominator. So the first thing we're going to find when we have the derivative is we're going to find the critical points. These are the max or the mins. This is where the slope is 0. So just so you can see it graphically, if I had a cubic function, I know this is rational, but I'm just sketching a cubic to illustrate my point, I'd be looking for these points, maxes and mins. This is when the slope of the tangent is 0. So what I'm going to do is I'm going to take this derivative, I'm going to set it equal to 0. That's how we find critical points, is we take the derivative and we set it equal to 0. Now I'm going to get x squared minus 1 squared. First thing we're going to do is we're going to put this over 1 and cross multiply. So we're going to get 0 equals negative 4x. And then I'm going to sub this back in and I'm going to get x equals 0. When I say sub this back in, I really mean divide both sides by negative 4. So we now have our critical point, which is x equals 0. Now we're going to go back to the original function and sub it back in to find the corresponding y coordinate, which if we look over here, we already did. So we know that the y-intercept is in fact also our critical point. So now that we have a critical point, we need to do a sign chart. And what a sign chart is it basically lays out the key values of x, where the critical points are, and identifies the slope in between them. And there's one of two possibilities between critical values. The slope is either positive or it's negative. We're also going to include the vertical asymptotes on our sign chart. So I'm going to draw this line here. This is like a number line representing values of x. I'm going to put a notch here for negative 1 because that's a vertical asymptote. I'm going to put a notch here at 0. That's for the critical point. And I'm going to put a notch here at positive 1 because that's a vertical asymptote. So what we're going to do is we're just going to literally plug in test values into the derivative function, which again is minus 4x over x squared minus 1 squared. So I can choose for this first number right here on the left side of the number line, I can choose any number less than negative 1. So I'm probably actually just going to choose negative 2. And if I do the math here, or do the arithmetic, and I plug in negative 2 into this function, I'm going to get positive 8 over positive 9. And just so you know, I plugged in negative 2 here and negative 2 here. So that means I have, when I plug in negative 2, I get a positive value. So I'm going to put a plus sign here and circle it. Now I'm going to choose a value between negative 1 and 0. And the only one to really pick here, to be honest, is negative 0.5. You could choose anything, but given that I'm doing the arithmetic in my head, negative 0.5 seems to be the easiest one. So if I were to plug in negative 0.5 in for x now, I would get, if you take a look, I would get, let's see, positive 2 in the numerator. And then on the denominator, I would have 0.25 minus 1, which would be 0.75. And then if I want to square 0.75, I'm going to get 0.5625. Let me just write that out. And again, because that's all squared, I'm going to have a positive over a positive, which means I end up with a positive number. Now, there's my critical point. So now I'm going to choose a number between 0 and 1. I'm going to get 0.5. So now we're going to plug in positive 0.5. And the nice thing here is the only thing that changes is the sign of the numerator. So that now becomes negative 2 over 0.5625, which gives me a negative value. What I really hope you're taking away from this is I'm not actually fully calculating or evaluating the expression. I'm just figuring out whether it's positive or negative. That's basically it. And that's going to tell me what the slope is. So here, I'm now going to plug in positive 2 because I want a number that's bigger than 1. And if I plug in positive 2 into my derivative, I'm going to get a very similar answer to what I had the first time, which was 8 over 9, except instead, the only difference is now the numerator is going to be negative. So it's going to be negative 8 over 9. So I'm going to put a negative here. So you may be asking yourself, well, how does this help me create a diagram? Well, I'm going to draw a little x-axis here. And there's another video on using the second derivative and putting it all together. But just so we can sort of see how this works. So I know I've got my vertical asymptote here, and I know I've got my vertical asymptote here. Here is my y-axis, and as we figured out above, I have a y-intercept at -2, so down here. And right away, I know the slope between these two regions here is positive. And so that means there potentially could be something like this. And the slope after this is negative, so it could be something like this. In fact, I'm going to clean that up just so it looks a little better like that. Because with rational functions, they tend to contort around the asymptotes. Now here they say the slope is negative. And when I say here, I'm looking at this part right here when x is greater than 1. They say the slope is negative. So that might mean I have a function doing something like this. And when they say, now, and I'm just circling that part, when we look at when x is less than -1, we say the slope is positive. So that means it's probably going up like this. And notice how I've drawn it such that I still have my horizontal asymptote at y = 0, which is right along the x-axis. So right away, based on the first derivative, we have a pretty good idea of what the function could look like, and we're going to confirm that by looking at the second derivative.